Yeah, thank you, Quan, for the very nice introduction. Hi, everyone. Today I'm going to talk about quantum algorithm for semi-definite programs with applications to machine learning. And this talk is based on three papers that was published at ICAP, ICML, and IIII respectively. So for the beginning of this talk, I'm going to introduce to you about semi-definite programs. So this is just the mathematical form that we are going to concern about today. So it's basically we are going to have a certain target matrix C here. So this matrix X here is a variant matrix. So the goal here is that we want to maximize the trace of C times X, and we have some such subjections. So one very important subjection is that we require the variant matrix X here to be a positive semi-definite matrix. And also on the other hand, there are also some other matrices like AI, and we require all the traces of AI times X to be smaller than BI. So this is the semi-definite program problem that we are going to concern today. And actually, it is a central topic in computer science and has wide applications. So for instance, this is a convex optimization problem. It is like one of the most important classes of convex optimization problems. And also, like SDP has a lot of applications from the perspective of algorithm design because it gave good approximations algorithm for the max cut, which is the Goldman-Williamson algorithm, and also for some constraint satisfaction problem, etc. And also, such kind of semi-definite program, like it commonly appears in operations research, in machine learning, etc. And also, on the other hand, notes that the semi-definite program contains a linear program as a special case. So it's also termed as the linear program, which already spans through all these kind of applications. Yeah, so let's talk about algorithm that can solve semi-definite programs faster. So specifically, let's specify the parameters here. So throughout the talk, we are going to use n to denote the dimension of the semi-definite program, basically the dimension of all the matrices X and AI and C here. And for this SDP here, you see that we have this kind of subjections. So throughout the talk, we assume that there are m subjections. And also for convenience, we assume that all the matrices are sparse, S sparse. So in the worst case, the sparsity, I mean, the number of non-zero elements in each row or column in the worst case can be m, but for many practical cases, this can be much better. So we also specifically denote the sparsity here. So the SDP is a really important problem in convex optimization, and it is well known because convex optimization can be solved in polynomial time. And of course, the SDPs can be solved in polynomial time. So because of the importance of SDP, people have been really pushing forward to give a very good algorithm for some SDPs. So classically, so on classical computers, the state-of-the-art algorithm with precision epsilon. So for with precision epsilon, it's just that you want to return a certain tilde x such that the trace value here is epsilon close to the optimal. To the optimal value. So there are different kinds of algorithm for solving SDPs, so depend on whether you want to get really good error dependence or not. So in the talk, we denote this gamma parameter here to be capital R times small r over epsilon. So this capital R and small r, you can just regard them as like the normalization factor for the problem, where it's just like the capital R here is just like the normalization factor for the primal problem here. And like for this kind of optimization problem, you can also consider a dual problem. I probably won't introduce the detail here, but you can also imagine that the small r is also like a scaling factor for the dual problem here. And epsilon is just the epsilon that I just mentioned. So in terms of gamma here, there are different kinds of algorithms that whether you really want to get good gamma dependence or you can tolerate some reasonably large gamma dependence, but you really want the dimension dependence to be good. So the state-of-the-art algorithm, I think, due to interior point method, I think it was like a stock paper this year or last year, and I think basically to keep the polylog gamma dependence, you can actually reach for the number of constraints m, you can reach m to the omega. Omega here is the current factor. I think it was also mentioned in David Gossa's talk earlier today. It is just a factor for the current factor for a matrix multiplication. So this m factor is just like m to the omega. And for n here is also like n to the omega. And this is basically the bound. If you want to have a good like polylog dependence in terms of the gamma factor here, this is a state-of-the-art result. But also on the other hand, if you are okay with some reasonably large gamma here, you can actually be much better in terms of dimension dependence. And this is due to a method called the matrix multiplicative weight method due to Aurora and Kali. You can see like this is really much better in terms of M and N. So it's basically like a linear dependence here. So because today is like the CFCS Quantum day, so for the quantum side, we are definitely interested in quantum algorithm for solving semi-definite programs. So we want to ask whether the quantum computers, quantum algorithm can solve SDPs faster than classical counterparts. So maybe yes, because like the linear program is really like a generalization of linear equations, and which can be solved like with exponential speed up by the HHL algorithm. And I think also in Andrew Chell's talk earlier today about differential equations, this is also explicitly mentioned. So our work is not like the first work that talk about like solving linear programs, solving semi-definite programs. So like the really first and seminal result was due to Brandon and Swart that they gave a quantum algorithm with complexity like square root of m times n times like s squared times like a quite large like gamma factor here, I mean the precision factor here, which is like to the 32 power. But you can see like this is really much better in terms of dimension dependence. I mean, compared to the classical state of art algorithm here, the M and N here, you see that really the quantum algorithm here get a quadratic speed up in terms of the M and N here. And later on, there is a work due to one Epperton, and I'll improve this to the same factor in terms of dimension, number of constraints, and also the gamma factor here is much better. It's gamma to the 8th. And also in the Brandon and Swart paper, they proved that there is actually a lower bound, a quantum lower bound for some SDPs, which is the square root of m plus square root of n. So you see that there are still quite significant gap compared to the previously known result and also the lower bound that they show. So the natural question here is that can we close the gap between the upper bound and the lower bounds here for quantum algorithm for some SDPs? So we basically figure out the answer here. So actually the true answer is much closer to the lower bound side. So we gave a quantum algorithm that can solve semi-definite programs with this complexity. So basically on the one hand, this is like a polynomial speed up compared to the classical bounds like this, like M and S and NS. So this, we really get square root of M square root of N here. And also like, which is better than the previously quantum result, we indeed get a quantum improvement in terms of the gamma factor here for such kind of factor here. So the classical, in the worst case, there's like a 7th power dependence, but in our situation is only like a 5th power dependence. And also compared to the previous quantum results, you see like the gamma factor is actually much better. So in this work, we use we want to get people we get people alerted that the quantum model here we use is slightly different and actually stronger than a classical counterpart. So classically, imagine that I tell you that this is a semi-definite program. Hey, just solve this. So how am I going to give you access to the semi-definite program? So the most natural way is probably just like some kind of entry-wise queries that you want to specify, like here is like a specific constraint matrix, and I have the row and column index of this constraint matrix, and you tell me what is the entry here. So quantumly, we assume the similar kind of the things that specifically you are focusing on like a specific constraint matrix, and like a row and a column number here, and you tell me the corresponding entry here in this constraint matrix. But with the extra assumption that this is actually a cheap instrumentalization, which means that you can you not only you can query for one place, but you can prepare like a quantum state and like get queries for this oracle instrumentalization. And also furthermore, because we have some sparsity assumption, you can also specify like which is like the non-zero entries in this matrices are, and this sparse oracle is also going to be something very important. Okay, so this is the result, and let me tell you something about how the algorithm is going to work. So the algorithm here is actually an iterative algorithm. So what do I mean by that? So it's just like for the SDP problem and in general for optimization problems, you are going to have a feasible set P here. You want to optimize a certain function fx with the subtraction set that the x is inside this set P here. So generic iterative algorithm with T iterations is just you're going to do this iteratively, and specifically at step I here, you are going to determine your xi here based on all the prior informations like xi minus 1 to x1, and also like the setting of the problem per se, I mean the set P and also the function f here. So in this talk, we actually consider like a reduction here. So we talked about that we want to solve an SDP optimization problem, but actually instead we only have to solve a SDP feasibility problem, that we don't have like optimization function anymore, but we have such kind of constraints, and also without loss of generality, we assume that everything is normalized, the trace of the matrix is 1. So why can we actually, without loss of generality, consider such kind of feasibility problem? Because we can just regard the target matrix C here as another constraint, and we just do binary search. So for instance, if you do the binary search, this is too large, then this problem just becomes infeasible. But if it's too small, this is probably more than feasible, and you really want to check for the wrap value. But this is just like a standard binary search that you can use the SDP feasibility problem to solve SDP optimization problem. And the rest of the talk, we are going to focus on this feasibility testing problem. Okay, so how we are actually going to do this? So this is really comes into this framework called the matrix multiplicative weight method. So as I mentioned in the earlier in my talk, this is actually due to a classical paper from Arora and Kali that gave a classical fast algorithm when the gamma is large. So the algorithm works like this. So initially, you don't have like a lot of information for the problem. So for instance, initialize the way that you're going to initialize is just maybe you start with the identity matrix. But when you move on for the algorithm, you just like test whether this your current solution, this WI, is a good solution or not. So if it is already makes the SDP feasible, then you are good. You can just like, so you already solved the problem. But if the SDP is infeasible, is at least if the current solution is infeasible, this means that there are some matrix that is currently violated. By violated, I mean that probably some of the inequality here is not true, where the left-hand side is larger than the right-hand side. So if something is feasible, that is something good, and you just pick that out. And this is how this is in the terminology here, just how we observe the game matrix here. So for each iteration, you are going to observe whether the current matrix is already feasible or not. If it is feasible, it's good. But if it's not feasible, you observe that, and you are going to update the weight matrix accordingly. So this is really like an exponential update with a minus sign here. So why do we want to do this? So we just want to, this is just like the multiplicative weight method, just like you are going to make some combination. You're going to make the final state to be the combination of the input matrices. But if something is really bad that currently makes your SDP infeasible, you really want to make the corresponding weight exponentially small. So that is the reason why we are going to have exponential here, and also like a minus sign here to keep everything moving forward, such that if something is not good, we make the weight to be exponentially small and make such kind of updates, so on and so forth. So actually, this is a really classical online algorithm framework, and actually suits the design of SDP feasibility problem very well. And actually, this is just like this just summarize what I just said, that if the current state is feasible, you just return, but else you just like move forward and make such kind of updates. So I guess this algorithm framework is quite simple, and actually you can show that it actually works very well for solving semi-definite programs, in the sense that the number of iterations, it suffices to be something really small, like 16 times log n or epsilon squared, can promise you to solve the SDP with a high success probability. But there are still something remain that we want to be careful about, that I think in particular, especially under already a very small number of iterations here, like log n or epsilon squared, we probably won't we won't pay too much attention into like improving the number of iterations. And actually in our work, we just don't have improvement on iterations. So basically we just honestly use this classical algorithm framework, but we look into what is going to happen inside each iterations. So we don't have any improvement in terms of T here. But what we really improve and we should really focus on is that there are two very important steps in this algorithm. So first step is just like we want to find a well-laid constraint for solving SDP feasibility testing problem, which is just the step for finding the game matrix here. And also for the second step here, so recall that basically for the algorithm framework, we have this weight matrix. It is super important that you can really make this a weight matrix up, because this is really like exponential of a certain matrix. And in general, I think for a classical computers, matrix exponentiation can be something very expensive. and in the worst case can pay like a time of matrix multiplication. And actually that is one of the reasons why many classical algorithms really have a cost like matrix multiplication here. So quantumly, we want to be careful about these 2 points about like how we are going to find a valid constraint and also like prepare such kind of weight matrix. And this weight matrix coincides with a terminology from the physics side called a deep state. So as long as you have like a bunch of matrices here, such kind of density matrices just represents like an equilibrium state of the system. And this is also known as a deep state. In my talk today, I'm probably not going to have a lot of time to explain the technical details, but what makes the quantum computer quite different compared to the classical computer is that we don't really have to do like a very laborious way of making a matrix exponentiation here. And actually for quantum computers, as long as all these matrices, they are well normalized, you can actually give a fast quantum algorithm for preparing the deep state, which costs only like tilde O of square root of n. So tilde O here just like ignores all the polylogarithmic factors. Another thing that we want to be a little bit careful about is the first step. And I think this for first step maybe is easier to digest from a high level perspective. That is to find a valid constraint in this SDP. So what kind of things are you like, maybe if you think about this, what is this similar to? You want to find something. And actually this is quite similar to the Grover search, but we want to search for some specific kind of things. However, here the thing is much trickier because it is not like a standard search problem because like everything is already there and you want to search for that. So here, everything here is just like you need to determine whether the current gas is feasible or not for each constraint in this SDP. So we have to do something much more clever. So you see like actually in the work of Brandon and Swart, their complexity is like square root of m times square root of n. That is reason. The reason is just like they use a naive way of using the Grover search that you just brute forcefully check all this whether all the constraints are satisfied or not. But actually, there are some clever ways of using the trick here. And actually, in our work, we call this like a fast quantum OR lemma. So the fact is that if you have a bunch of projectors and also you have such kind of like parameters here. So actually, if it is like an extreme case that whether the trace is quite large or the sum of traces is quite small, you can actually make a test that only using one copy of the state to decide which is the case. And in total, it's only like a square root of m operations surfaces. So there are actually some technical details that I'm not going to explain today. But in fact, actually, we just have a good design about how we are going to call this kind of, I would roughly speaking, say this is like an operator version of the Grover search, how we are actually going to call that, and how actually this is a very important thing that we can make the decoupling between like these two parameters, like from square root of m times square root of n to like square root of m plus square root of n. So this is just like operator version of the Grover search. So I guess this is a place that maybe I can pause a little bit. And is there any quick question here? Okay, so maybe if there is no question for now, let me continue to the application side. And if there are any questions, just feel free to ask at the end of the talk. So what I have just been talking about is a specific optimization problem, the SDP problem that the quantum computer can really solve very fast. But this is still quite like abstract and really on the optimization side, which is a theoretical result. For the application side, I think a very natural question to ask is that can this be applied to solve some, like, I won't say this like real applications, but we really want to turn to at least a little bit more practical side. So for instance, like the SDP have valid applications in machine learning. So can we really deal with some problems that commonly happens? So I think this kind of very general questions we can always ask, but we also want to be clear about whether these kind of questions we can really deal with them. So I think a very important point, I think from a technical perspective, is that this matrix multiplicative weight method is actually very similar to playing games in the sense that in the algorithm framework, we update the weight and actually in the quantum size density matrix according to the answer of the previous round. So if something is like some constraint of the SDP is infeasible, we don't like it and we make the weight getting smaller. So this is just in general the way that we are changing the strategy. But I think maybe we want to, in general, formulate the problem as follows. That maybe this is just in general like a minimax optimization problem. So like one side we can design our quantum algorithm, but also on the other hand, there are some really constraints that we really want to deal with. And such kind of minimax optimization problem that is like very abstractly written down like this kind of form. This is like actually going even much beyond what I just discussed about semi-definite programs. It actually appears not only like in game theory, of course, for the minimax problem, but also like in economics, in operations research, in deep learning, for instance, like generative adversarial networks, the GANs, etc. It's just like minimax optimization has so many applications in real world. So in the rest of my talk, I'm going to discuss about how like my quantum algorithm for solving semi-definite programs and in general such kind of ideas can be moved forward to the side of machine learning. So we are actually going to begin, because semi-definite program is like a matrix problem. So here we are also going to discuss something a little bit simpler, which is called a matrix game. So in the worst case, I mean not the worst case, but in the general case, the minimax optimization problem can be a quite arbitrary function here. But for the rest of my talk today, I'm going to talk about matrix games, where it is actually quite nice in the sense of being bilinear, that the mean part and also the maximum part, they're actually vectors here. So matrix A here, some matrix like n by d, a matrix. The vector x is taken from some set of is taken from a set x, which is a subset of r to the d, and the vector y here is taken from a set y here, which is a subset of r to the n here. And actually, this is bilinear in the sense that everything is linear. So if you make some linear combination here and also some linear combination here, the value here is actually also going to be a linear combination of the things that you choose. So such kind of bilinear matrix minimax game is, of course, it is a zero-sum game, and it is also a very important kind of a zero-sum game. But actually, it already covers a lot of very important scenarios. So for instance, like from the point of algorithm design, such kind of bilinear minimax games, the matrix game is equivalent to linear programs. So that is really good. We are talking about semi-definite programs, and this is just equivalent to linear programs, which is a special case of the semi-definite program. And also from really the point of machine learning, it contains like linear classification as a special case, and also has a bunch of different connections. So in this talk, we are basically talking about the computational cost or complexity of solving all these kind of problems. And actually for a matrix game, it is a folklore result that basically matrix game can be solved in linear time. The linear time is meant by the size of the matrix A here. So because the matrix A here is an n by d matrix, so it is by solving in linear time, it's just like we probably just need to read through the matrix A here, which already costs like O of n times d. And in general, this is a folklore result that this n times d suffices to solve the matrix game problem. But actually, we want to be a little bit more aggressive here, that in general, can matrix game be solved in sublinear time? I mean, faster than the scaling of the, sorry, not the scaling, but the size of the matrix A here. So this question can be a little bit aggressive, but there are some prior knowledge for that. So these two bounds are both classical results. So actually, it is known that for the matrix game, there are scenarios where even classical computers can give a sublinear algorithm. So in particular, we consider such kind of minimax problem. And actually, we assume the further assumption that is made in this minimax matrix game is that we assume that both the x and y here, they really actually have a good norm dependence. So for instance, like the x, if the x and y here, they are both L1 norm unit balls, and actually it can be shown that the n times d bound can be improved to n plus d times like a log factor of epsilon squared. And also it is known that if the x here is taken from L2 norm and y here is taken from L1 norm, then the bound is also like something like n plus d times log n over epsilon squared. But you see, like these two are really very special cases that it is actually we are talking about only L1 norm and L2 norm, and you know, like for L1 norm, this is very special. For L2 norm, it is just the Euclidean space. So that is really nice. And I think a very natural question here is to ask is that how about like general matrix, a matrix games and other metrics? So what if we are not only restricted to the very special like L1, L2 norm, but maybe some other kind of matrix norms can we actually still solve the matrix game in some linear time? And furthermore, because we are talking about quantum algorithm here, so can quantum algorithms of such kind of matrix schemes even faster? Yeah, so I'm happy to tell you that we can answer these two questions affirmatively. So our first contribution is that we gave a classical algorithm for solving general matrix schemes, which actually works for general matrix. So in this work, we talk about there are two parameters. So this we have the parameter q here, which is between 1 and 2. And this p is somehow like a reciprocal compared to the q here, which means that 1 over p plus 1 over q equals to 1. So in this work, we consider like LQ, L1 matrix scheme. So basically, you see like the P here is still taken from the L1 norm ball here. But here, the X here, we can really take it from some arbitrary norm here. As long as this Q is between 1 and 2, we can actually consider such kind of minimax matrix scheme here, which is follow this LQ, L1 norm. We can actually show that we can solve such kind of matrix scheme with a precision epsilon. With high success probability only using this number of time, which is actually quite similar to the previous bound, but we want to be a little bit careful because there is a factor of p here. So in the sense that if this q is really, really close to 1, this value of p can be large and can somehow influence the game. But actually, on the other hand, if this q is too close to 1, you can roughly speaking just regard this as an L1 matrix scheme. You can actually also still solve it quite efficient. So this is not a big problem, but just like a caveat here that people want to be careful about. So on the other hand, in our paper, we show that this bound is actually near optimal, that as we can prove that this n plus d is like neither n nor d can be improved, that it should at least both of them should be at least linear in the sense that we can prove n plus d classical lower bound here. So the core idea here is actually for this minimax game, you can imagine that this is probably going to be the algorithm is going to be a little bit more complicated than the matrix multiplicative weight method for solving semi-definite programs, because it is a minimax problem and there are two sides. So in general, the idea is that we are going to have like an algorithm with double loops, and in general, one loop for the primal and one loop for the dual, and this is just called the primal dual approach. And we follow close to the classical L2, L1 matrix scheme work due to Clarkson, Uldorf, and Hazan. We follow that work, but we make some updates. So in their work, it's just like their primal dual approach. So both the primal and dual in their work actually use the multiplicative weight updates. The main difference compared to them is that for the primal part, this is using some well-known technique called online gradient descent. But for the LQ, L1 norm here, we really have to make some modification. And I think we really get a brand new version of the algorithm framework using the mirror descent method. And actually, we specifically use the LP version due to Shalav-Shvaz. So roughly speaking, I would say, like intuitively, this sounds like an interpolation between the L1, L1, L2, L1 matrix scheme with like some non-trivial technical contributions in the primal dual approach. So maybe let me actually show that how the algorithm looks like here. So you can see that this algorithm looks like a little bit familiar, maybe compared to the previous SDP algorithm for matrix multiplicative weight update. But here there's not like a matrix update. It's just like the standard multiplicative update for vectors. Because here, like both like the x and y, the size here they are taken for vectors instead of like density matrices. So this makes the algorithm looks a little bit simpler. And actually, you see this algorithm, indeed, it has double loops. So this part is like for the primal, and this is like for the dual. And for their framework, the update is not exactly exponential update, but somehow it's not like exponential update, but we want to be careful, especially for this LQ-L1 matrix scheme. So what we noticed that the best thing that we should do is to use something like really depends on LQ norm here. Basically, we make some kind of LQ norm here, and also we make a clipping to make sure that the function is not really getting, because you are dividing something here, it's not really getting something too awkwardly large. That is something we really want to get rid of. And also there is somehow like the quadratic update here. And also for the primal part is also because for the dual part we use some LQ norm, and for the primal part we use some LP norm. And this is really somehow like a mirror descent that commonly appears in optimization literature. But actually, this is this kind of improvement compared to the previous algorithm really does the job for solving such kind of general matrix schemes. So the next question here that we want to address here is that we already introduced a brand new classical algorithm for solving general matrix schemes. So next question is that whether quantum algorithm can do the task like even faster. So I'm happy to tell you that it is. So the quantum algorithm is just like this statement is similar, it's just the same compared to our classical statement. But we want to be even better in terms of the quantum bound, which actually we are happy to tell you that for both the parameters n and d here, we are able to achieve a quadratic quantum speedup. So in terms of n here, the square root of n, and this also square root of d here. But the epsilon and also the p dependence here is unfortunately a little bit larger. So epsilon here is the epsilon to the 4, and epsilon is like a 7th power here for the d parameter here. And then so the p here also have like a polynomial degree here. So this is a little bit worse compared to the classical bound. But recall that classically it is shown that n plus d is a solid lower bound. And actually the quantum bound here really improve upon the classical counterpart. So and also in our work we proved that square root of n plus square root of d is a quantum lower bound. So which means that our quantum algorithm is optimal in terms of these two parameters. So let's briefly highlight our quantum algorithm here. So there are some really good things. So I think one thing is that we really have some standard quantum input. So this is just Schrödinger's cat here, but as you can see that this input is just the same as the input that we use for solving semi-definite programs, where it's just like you can query if just like a specific entry according to the row and column of the matrix, and you can just query for such kind of entries in terms of row and column in serialization. So a very important thing that a very important advantage of our result from my perspective is that the output of our algorithm is classical. So you can see also this is actually demonstrating the statement of the theorem here. We actually don't output like something quantum, like a quantum state, which is happened in the HHL algorithm. But actually we output something classical. We output a classical succinct representation of the solution. And I think this is quite good compared to a lot of other quantum machine learning algorithm, because the classical outputs is probably very, very good in the sense of being suitable for end-to-end machine learning applications. So the speed up here is that you can just imagine that it is actually based on our classical n plus d algorithm, which is a primal dual approach. The primal is a multiplicative weight, and also for the dual is online gradient descent. So we just like for both of them, we achieve a quadratic quantum speedup. The MW part, the multiplicative weight part, is just quite similar to the way that we improve the classical SDP algorithm. But for the online gradient descent here is something a little bit different. So this is like a quantum algorithm for LP sampling of quantum states, and I will discuss about that in a minute. And also, as I just mentioned, that this is our quantum lower bound is matching the quantum upper bound here. So the LP sampling of quantum states is something like this. So if you're familiar with the HHL algorithm, this is actually quite similar to that. So we just like, we have the quantum oracle here. We can first like prepare a uniform serialization here, we query the oracle, and we just like make some phase rotations. But we want to be careful that the phase rotation here should be represented LQ norm here. So we just rotate according to the LQ norm, and then we uncompute the oracle here. And after making such kind of like that phase rotation in terms of LQ norm, we furthermore apply the quantum amplitude amplification to amplify this part of the quantum state with the second register being 0, which is the part we want. And finally, we are actually going to return a quantum state, which is basically having the form of this part with high success probability. So this is actually how we are actually using. For the MW part, we use the previous improvement, and for the dual part, this is how our new algorithm plays a role. Okay, so I think this is for the matrix scheme, and I think for matrix scheme is already quite, I think from my perspective, quite intriguing. But also we want to furthermore discuss about some applications. So one important application in our work we show is this approximate Carat-Theodore problem. So the Carat-Theodore problem is a very important problem in convex geometry. So the point is that for convex geometry, maybe you have like convex hull of a bunch of vertices. So now you are having like a point inside the convex hull, And I think in general, it is known that if the convex hull is of d-dimensional, you can always like make a linear combination. Every point inside a convex hull of d-dimensional can be written as a linear combination of d+1 terms. But can we do this a little bit better? So for instance, you can tolerate like an approximation error here. So for instance, like for this convex hull here, representing u can be expensive. But if you tolerate like a small epsilon here, this u prime can actually be approximated by linear combination of only two vertices. This is much better than like a very complicated linear combination of the original point u here. So in our work, we show that for this approximate Carat-Theodore problem, there exists a solution with like a linear combination of only using like a p plus log n over epsilon squared number of vertices of the convex hull. And actually, this approximate Carat-Theodore problem can be solved in sublinear time, which actually we just make a reduction to the matrix scheme, a general matrix scheme. That in general, for the classical algorithm, we have this cost, and also for the quantum algorithm, we have this cost. And similarly, this general matrix scheme that works for general matrix can also be moved forward to solving some really machine learning problems, especially the support vector machines. So in our algorithm, we show that even this margin is something different. For instance, like like LQ version of the margin here, we can actually show that we can solve the support vector machine with a sublinear time classical algorithm, and also a quantum algorithm with this cost. Okay, I think this is probably close to the end of my talk, and also considering time constraint, I should wrap up. So today I actually talk about like I was like roaming through a few different things. So at the beginning of the talk, I talked about the quantum algorithm for solving the following semi-definite program, and actually this algorithm has complexity like this: square root of m, the m being the number of constraints, square root of n, the n being the dimension dependence, and this gamma factor is like this r over epsilon, which is roughly speaking just like a renormalization factor for the problem. And actually, we use the same spirit to solve a closely related problem for matrix schemes, especially the general matrix scheme having this kind of form, where I think compared to the previously classical result, we can move forward from only like L1 and L2 metric. In general, we can talk about LP and LQ metric for the problem. In general, we give a classical algorithm with a sublinear cost, which is improved upon like previous classical results. And also we gave a quantum algorithm that was cost only like a square root of n plus square root of d, which is also like a quadratic speed up compared to the classical counterpart. And also, as I just mentioned, it can be very naturally applied not only directly to some matrix scheme, but also like a problem in convex geometry, such as the approximate Carat-Theodore problem, and also the machine learning side, such as like LP version of the support vector machines. Okay, so this is the end of my talk, and thank you for your attention.